record on this computer. All right, is everybody able to see my screen okay? I'm sure you are. I just want to confirm.
Yep.
All right, so I'm going to be talking about module 4. I still have to set the due date and stuff for it, but it's going to be a bit of time of time. So let's see. For module 4, you have 2 assignments that you can choose from. Now, as I explained last Thursday, both of them use the same core file, which is circularlinkedlist.java. So I'm going to go through and I'm going to go through the file, and I'm also going to go and so I'm going to go through this file, and I'm going to go through the assignments. File, and then solitaire encryption has an additional file. Okay. There we go. And there we go. So let's see. Then I use, let's see, stop sharing for a second. All right. So first, a brief overview of these files. Okay. First is the circular linked list file. It is a for the most part, I've created, and you've only got specific places where you want to change things. It implements iterable, which means you can create an iterator. Technically, you could use a for each loop on it, but I wouldn't recommend that because of the way the iterator is constructed. So I've set up your instance variable and your instance variables for you. You'll have a constructor. And then I have other things to for you to fill out. I've got the get node method, the add method, the other add method, and the remove method. Now, the toString method is deliberately designed so that if you mess up in your add and remove methods, it will crash your program. That's a feature, not a bug. If your string, the way this toString works, when you try to print your circular linked list, it will do the following. If your circular linked list is size 0, return nothing. Otherwise, return the first thing in the only thing that's stored in the list if it's size 1. Otherwise, basically it starts at the first item, and then it goes to the next item, and the next item, and the next item. So the place where a circular linked list differs from a linked list is that normally you start at the head, you go from item to item to item, or rather from node to node to node to node to node until you get to the last node. And that node normally points to null. In a circular linked list, that node points to head instead, making a circle. So we stop our loop once current is equal to head. So this will break if your circular linked list is messed up, or it will display weird missing numbers and weird swaps otherwise. So watching my videos, if you haven't already, will be extremely useful for this lecture. The get node can be done pretty much the same exact thing I did in my lecture. We need to switch this false to true in order to get it to be a correct for the add method. And then for the add and remove method, that's where the bulk of Josephus or about half the work for Josephus goes on. Half to 75%. You've got 5 cases for doing add and remove. if we're adding an item and the index we're displaying is out of bounds. If we're adding an item, but the list is empty. Adding an item to the front of the list, adding an item to the back of the list, and then adding anywhere else. So the big thing about this is that if you set this up as 5 separate if statements or if else statements, they are mutually exclusive conditions. For instance, adding to an empty list would, you got to make sure that if you're adding to an empty list, you're not also adding to the front and the back. So you want to do if, else if, else if. But it also means you don't have to worry about like these edge cases otherwise, because we're setting aside our edge cases here. Similarly with remove. These will follow similarly to what I did for a doubly linked list and the code I did in there, with 2 large exceptions. Doubly linked lists have every node in it has a forward and a backwards pointer. And also every node, so we don't have those here. And the second thing is that whenever we change the head or the tail, we need to make sure that the tail points to the new head. So it's got to be kept consistent like that, which does not take too long. So the other thing I created is that this list iterator, it's more useful for the Josephus problem, figuring out how it works. Or rather, use and the PDF does go over how to use it for the Josephus problem. You don't really need that for the Josephus problem. If you're not doing the Josephus problem, what I highly, highly, highly recommend doing to make your life about 20 times easier for the solitaire encryption problem. So if you're not doing the Josephus, you're doing the solitaire encryption instead. You will want to add a public get method, get int index. And if you haven't watched the videos yet on linked list, this is probably a bunch of gibberish. That's fine. It will make sense once you do. So you want a get node, you'll want to do a get and a set method for your solitaire encryption. All right. The solitaire encryption file, for the people who want to do the solitaire encryption instead, I've created these 2 things for helping with decryption, which I'll go over in a bit. And then you have 5 steps you want to implement in this. So about a good portion of the work is done with this file once you've finished the circular linked list. So let's go over what the assignments are. So this the Josephus problem is named after Flavius Josephus, or Yosef ben Matanyahu, as his Hebrew name, but he's more known by his Greek name, Flavius Josephus, a Romano-Jewish historian, as it says. And what it is basically is a bit of history. It's got a bit of story behind it. Josephus, its name, basically there, so you may be aware there was this huge thing called the Roman Empire. And it was pretty large. It spanned a lot of Europe, parts of Asia, parts of Africa, I think, Middle East, got all the way to Britain, pretty big. Empire building is one thing, but empire maintaining is another. Maintaining an empire is pretty hard when you've got a lot of people and messages can only travel as fast as people can. So, and a lot of people rebelled against the Roman rule. There was a Jewish uprising against the Roman Empire, and it ended the way most revolts against the Romans ended, extremely poorly. So Josephus was both a priest and a war leader at the time. So, and he was leading a war band, and it got surrounded. during the siege of Yodfat. So him and 40 other soldiers got captured by the Romans. And what happened next is pretty dark and grim. Just be aware of that. They decided that basically that they'd rather die than be captured, because captured meant slavery, being enslaved by the Romans. So they rather die as free men. So what they did is that they drew lots and then killed each other by drawing lots, by some not really ever clearly known method, but the Josephus Problem is basically about figuring that out. But anyway, so Josephus and one other person was eventually left standing. Then they looked around, and they said, well, this was a terrible idea, and surrendered to the Romans. So Josephus became a slave, and he gained his freedom a few years later. So surrendered in 67, year 67. And then when the general that captured him, when the general became the emperor in 69, he became free, and he assumed the family name of the emperor. So why he's a notable figure, though, in terms of history, which is and this is why it's worth knowing about him. It's because he was a historian. And I mean, historians are not exactly super common back in history, I guess. Because we don't have too many documents, but he wrote about the Jewish War, the antiquity of the Jews. And he also, but most notably for historians of religion, he wrote about first century Judaism and early Christianity, because that's when basically Christianity got started. And so that's when it started becoming a thing. And these are extra biblical accounts, meaning outside the Bible, for people in the Bible. So very interesting, basically being able to see what parts are history, what parts are religion, those kind of things. So it is interesting as well, because also, right, back then, there wasn't really much peer review, I guess. So it's just very interesting to note what he read, if you're interested in history and that kind of stuff. But the Josephus Problem is about this whole drawing lots thing. The way that basically that historians think that lots were drawn was that basically they stood around in a circle and waited to be executed. And what they did is that they basically started at the point in a circle, and basically they counted, this one does step size 3. So they basically would remove every third person from the circle. So 1, 2, 3, 3 is removed. 4, 5, 6, 6 is removed. And it goes around and around every 3 people until we go back around 39. The 40th soldier is spared, the 41st soldier is spared, but the first soldier is not spared. It keeps going around until there is 1 person left. All right. So the question is, for this circle, if given a circle of size n and a step size of k, meaning we are removing every kth person from the circle, where do you want to be in the circle in order to be the last person standing? Now, the interesting thing here is, now it's a pretty interesting mathematical problem, even if it is a bit morbid. And I make no mistake, it is a morbid problem, which is why we typically reduce it down to a counting out game where people are standing in a circle and try to guess where the last person in the circle will be. And there's a lot of analysis for a step size of k is equal to 2, so every other person is removed. And a lot of code around that. And you can use modular arithmetic and some fun math to figure that out. But we're interested in the general case, which has this wonderful looking equation down here. Given a circle of n people and a count of k, then this equation over here tells you what the last person, where the last person will be removed. And that's super clear to everybody, right? Super understandable. So so for the Josephus problem, we're not going to do this problem. We're not going to do this math. This math is messy. We have a circular linked list. So we can easily remove nodes from a list, no problem. And since it's circular, we can keep going around and around it. And that makes it like, we can simulate this. Why do the hard math when instead we can simulate it instead? And so that's what the objective of our Josephus problem is. Not only does Wikipedia have a good article that the computer file, but I can't remember if it's a number file or a computer file because they do the same. They're the same people, I believe. They have a very good video on this subject as well. And I provide the code. I provided and I've provided some sample outputs of what you should basically expect to see. And note that I'm starting with 1 as opposed to 0 here, just because that makes sense in the way people count. All right. So the other problem I have is, so any questions on the Josephus problem? And I want to remind you, you get to choose which of these 2 problems you want to do for homework. Okay. And you'll have longer than a week to do this because these are bigger problems. Any questions on this one? Or have I totally just like lost the thread of things because it is a very weird problem? Man, it is so just an aside, it is so weird talking over Zoom, and I can't see anybody's faces because I can't gauge reactions. You don't have to, thanks. So Nathaniel, is there something you want me to clarify for you? Basically, again, you're just imagine you're standing in a circle and basically you're just trying to guess where the last person in the circle is going to be removed. You remove every kth person. And we're not going to try, again, we don't want to try to figure out the math behind it. The math is hard. Leave that for the mathematicians. We're doing computer science. Makes more sense for us to simulate this thing.
I have a question.
Yes.
Could you scroll down to one of those examples? There was one that had like 1, 2, 3.
Oh yeah.
5.
So here, n is 5, k is 2. So this is the initial configuration of the ring. So we count, and we're removing every other person, every second person. So 1, 2, 3, 4, 5. So we count 1, 2. We remove 2. Then we do 3, 4. We remove 4. Then 5, 1. We remove 1. Then 3, 5. We remove 5.
Okay. Thank you.
And this is the way it works for, k is 13. And again, I've already created the Tostring method for you. So basically just printing out your ring every step, your circular linked list, every step will produce something like this. Because that helps normalize it. So I know what I'm looking at, but also, again, it's specifically designed to crash if it's not working. All right. So this problem is worth 200 points. It's worth twice as much as the normal homework because I consider it to be like 2 homeworks worth. The other problem, Pontifex, is worth an extra 20 points. So you get 220 points out of 200 if you decide to do the solitaire encryption or Pontifex. So the name Pontifex comes from the fact that it's from a book. All right. So I totally got this problem from somebody else, but I've read Cryptonomicon, very good book. So I'm a fan of Neil Stephenson's work. He writes these big door stoppers of books. And if you're interested in reading some of his works, I highly recommend the starting point of Reamde. That's REAMDE, which is a misspelling of readme. Because it actually, reads like a techno thriller, that he goes into extreme detail about things, such as what hackers like to do. They like lockpicking, and extreme minutia on the way certain weapons work, and how much force is required to pull triggers, because he does his research, and then the research makes it into the book. And the reason I suggest this book is that other books of his, they don't really end as so much as his editors get sick of reading his work and tell him, we're just stopping here. Because he has not always been good at doing endings. But for that one, for Reamde, it's good. This one comes from his other famous one, which is Cryptonomicon, which is pretty also worthwhile if you're a computer science person. So the idea here is that you want to send an encrypted message, but you're worried about your computers being being infected with some malware or the like, and you can't really bring a one-time pad, which is the only really secure way of sending messages, because somebody could intercept that one-time pad or take it from your bag or something like that. So you need a way of creating messages that looks innocuous, but we can use it to create encrypted messages. And it turns out a deck of cards is pretty perfect, because they're of a wonderful, wonderful coincidence that's just too wonderful not to use. You see, the English alphabet has 26 letters. And a deck of cards, if we take out the jokers and the nonsense cards, has 52 cards in it. 26 times 2 is 52. So twice as many as we need. So we can so this allows us to do some fun things with this. So Emil Sivertson, of course, actually wanting to make a real life algorithm, not just say, oh, we used a deck of cards, actually contacted Bruce Schneier, who is very well known in cryptography circles, to actually write this algorithm. The novel has a description, but we are basically going to be using a simplified version of it. The idea here is that you can carry around a deck of cards with you, and you can memorize a configuration of this deck of cards. For simplicity's sake, we're going to be pretending that a deck of cards only has 26 cards in it. So we're only using a half deck, maybe only all the red cards, but that's simple enough. Okay. And so we'll take those 2 cards and the 2 jokers. Sorry, those 2 suits and the 2 jokers. So furthermore, we're going to give everything values. So for instance, Ace of Hearts is going to be 1, 2 of Hearts is going to be 2, 3 of Hearts is going to be 3. Then we're going to go all the way to 10 of Hearts will be 10, obviously. And then when we get to Jack of Hearts, we'll call that 11. The Queen will be 12 and the King will be 13. This allows us to stop thinking about this problem in terms of cards, and instead we'll think in terms of numbers. And for what we'll do is say our next is spades. Ace of spades will be 14, 2 spades, then 3 of spades will be 15 and 16 respectively. Okay. The point being is that we can just use the numbers instead, which is good. So what we do to cryptography, well, this actually begs the question, how many of you have actually done cryptography at all? None whatsoever, as expected, which is great. So now for a crash course on cryptography. The history of cryptography is intricately tied with one subject, and that is the subject of warfare. A lot of war in this lecture. We're talking about Jewish revolts against the Romans, but we actually do have to go back to the Romans again. Yeah, RSA is interesting, but it requires like nasty math that you aren't comfortable with until you're really comfortable with modular arithmetic. I believe. But the point being here is that the Romans had basically had the first big cipher that was really in well use, which was named after Caesar. This is the Caesar cipher, the Caesarean cipher, also known as the shift cipher. But basically, the idea here is that we would send our messages in Latin. Now, barbarians, being people who couldn't now barbarian being technically defined as somebody who could not read Latin, although barbarians were previously defined as people who could not read Greek or speak Greek because they all said bar, 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 bar. I think I'm making that up. Let's check. Barbarian. From the term barbaros. In ancient Greek, Greeks used the term towards people who did not speak Greek and follow classical Greek customs. In ancient Rome, Romans adapted and used the term towards tribal non-Romans. Etymology. According to Greek writers, this was because the language they spoke sounded to the Greeks like gibberish represented by the sounds bar, bar. Not making it up. So barbarians, people who cannot speak Greek. So your barbarians, in the literal sense of the term, was basically not necessarily expected to be able to say you send out a scout with a message. The barbarians capture your scout and read your message. That's assuming they can read, because that's few and far between, but that's enough that you have to consider it. If they read your message, though, then your plans are foiled because they can either not be there when you attack, or they could set up an ambush. So you got to protect that message in a separate way. So encryption. The idea here is that if I'm going to write so we do hello world in as our basically first thing for programming. Encryption has a similar term, phrase. This is the hello world of encryption. Attack at dawn, because it's very much a message that you might want to send if you're at war. Okay, and the idea here between the Caesarean cipher is that things are shifted a certain amount, either typically 3. So here, this is shifted to the right 23, which is the way I typically do it. So A, the letter 23 letters after A is X. So instead of writing A, we would write X whenever we had an A. So X is instead in my message. And then let's see, the T would be Q's. So I would write this. And the C would be Z, and the K would be H, and the T would be another Q, D would be A, W would be T, and N would be K. So our barbarians would read this message, and they'd read this, and they'd be going, did they just like, I don't know what this is. You know, they'd probably say something something non-complimentary about the Roman general's mental state, and then move on is the idea. Or they would figure out as a coded message and try to crack it. But the idea here is that encryption is a new concept here. So the idea that this is encrypted in some way is difficult to crack. However, notice the way we're just rotating letters like this. Okay, there's only like 26 possible ways we can do this rotation. Now me, the general, how do if I receive this message, how do I decrypt it? Well, I can either work in reverse by subtracting 23 and going back, or I can do what might be a bit easier, since I said, okay, we already set up that our encryption is 23, so I can add 3 to make 26, because if I did an encryption of 26, that would go all the way back around to A. Make sense? So adding 3 to X would basically say, okay, X brings me to A, Q goes to T, So because QRST 3 after, and then I'd be able to decrypt it. Okay. So for now, for as long as cryptography has existed, the art of making codes, we have gotten things like cryptanalysis with the art of breaking code. Again, not too hard to break the Caesarean cipher because you've only got 26 possible combinations of this. Up through World War I, this was the state of the art, which was called the Veneer Cipher. 1553, and then it took until about, and it stayed safe for about 300 years before there was a way to break it. And the way you break this thing is by basically fingerprinting the language. It's a very interesting topic using statistical analysis. Every language has a fingerprint, and you basically look for something that gives you that fingerprint. So again, here's our hello world. We have the plain text encrypted as attack at dawn, but instead of giving it one key, right, shifting everything by the same number of letters, we're going to shift everything. We're going to shift different sequences. So for instance, I'll use a keyword like lemon, and basically, okay, A has a certain numerical value, L has a certain numerical value, and I will shift by however many letters by whatever L is. Make sense? So over here, that would be, and typically there's a table that you use to do this, to figure out what you're doing. So attack at dawn gives us limit, and then basically we'd have a sequence of repeating keys. Lemon, lemon, le. We just keep repeating it until our message is done. And it's much stronger than the Caesarean cipher, because instead of 26, instead of 26 possible keys, your keys are the number of words in the entire alphabet, or possibly a passphrase. So here, attack at dawn, lemon, 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 and that would become this ciphertext. I'm skipping over how that is done. That is not relevant. But basically you could still send a mathematician upstairs with basically whatever he needed to get his work done, and he'd come back down in a couple hours and basically hopefully have a cracked message soon enough that you could use it. It was still crackable by hand until we got to World War II, where machines started to be used for encryption. And so machines started to have to be used for decryption. So this is kind of a throwback because we're not using machine for encryption. We're using cards for encryption. But the key here is that every letter is given a key. And the idea here is that I have also on new share, I have already created the function that says, given a letter and given the key, it will give you the encrypted character. Give me a letter and give me an encrypted letter and give me a key, and I will do the math to decrypt it for you. So I've already done that part for you. The part of basically saying, here's a letter and a key. The key being a value between 1 and 26. Okay, so going back to the problem. Everybody can see the PDF again? Okay. So the idea here is that rather than memorizing a word, I have to do something annoying, but worthwhile, which is memorizing a specific configuration, starting configuration for the deck. So I will basically remember 26 numbers, in the numbers 1 through 26 in a specific order. That's hard, but you can do that with work. Okay, well, specifically you memorize the configuration of 26 cards and the 2 jokers. So the way this works is 5 steps, and we'll see this in practice, okay, through a video. We have our numbers as 1 through 26. We have the joker as, we label the two jokers as different values. Typically, a deck of cards has two jokers in it, one of which is color, one of which isn't. Okay, that was the color one. Here's the black and white one. So you have two jokers, you can tell them apart. We'll just call them Joker A and Joker B. The steps are basically as follows. Find the first joker, swap it with the card beneath it. Next one is find the second joker, move that joker 2 cards down. Next is we perform a triple cut, where we take all the cards above the first joker, all the cards below the second joker, and swap those to the position of all those cards. The third is a counting cut, which is we remove the bottom card of the deck. This is the Jack of Hearts, meaning it is an 11. And what we do is that we count the top 11 cards of this deck, put them over here, put the Jack back on. I'm going through this quickly because it's much more easier to see this in example. And then finally, what we do, after doing those 4 steps, we can finally figure out what our key is. We look at the top card of this deck. We see it's a 6, so we count down 6 cards. 1, 2, 3, 4, 5, 6. We see we'll pretend it's the Queen of Diamonds, but we'll pretend it's the Queen of Hearts, which would make it a 12. So our key is 12. So our first letter would be modulated by 12. We keep the deck in its current configuration, repeat the steps again for every single key we want to generate. That's a lot to take in. So fortunately, though, someone was kind enough to produce a video showing how this works in practice. So new share, optimize for video clip, share sound. Actually, we don't really need to share the sound over here. All right, so can everybody see the video just fine? Let's see. So, all right, can you help create a book for aside from my book, Cryptonomicon? Sure. The idea here is that phones are easy to grab, but and you want to spy them, but cards are innocuous. So the idea here is that we are basically replacing one word by one letter by another letter. Oops. All right. So it's not at all related to the game of solitaire, other than it just involves cards. So here they're doing they're using a full deck of cards rather than the half deck that we're using, but the same thing applies. So how to get a key stream. So this is the way it works in practice. We take a deck of cards. You label your jokers in case they're identical. So she labels them A and B. Okay. Puts them into the deck of cards, shuffles it up to just kind of, and then we pretend that this is now a sequence that we have memorized and that our partner who wants to decrypt also has memorized. So the first thing we do is we take the first joker, move it down a card. Then we take the second joker, move it down 2 cards. Step 3 is the triple cut, where we're going to take all the cards above the first joker, doesn't matter, and then take all the cards below the second joker and swap them. So see that what was on the bottom went on the top. Now, this is where I need to mention why we're using linked lists for this. Linked lists are great at that kind of operation, where we are taking a single list and splitting it into multiple lists. Array lists are terrible at that. Count cut. Look at the bottom card, remove it. So according to her, the way she assigned values, she counts as many cards as that is, which I think would be 26 plus 8, moves them down below. And then the last step, generate the key stream number, 9 of clubs. And so she just simply counts however many off that the 9 of clubs is. And so our value is 7 of clubs. Now, without reshuffling, we keep doing this for every number. So here she is already doing a triple cut again. Once you know how to do it, it's actually fairly quickly. She'll go through it and generate them all. And so, and then here we go. And then she gets her encryption values. So on that one, so that one looks more intimidating than it is, but it is, you know, a bit of work to try to figure those out. So for instance, swapping step 1, step 2, step 3, step 4, we used it. So for a lot of test cases, we use this sequence. You'll want to test your code on this sequence of cards where every value is basically we add 3 to each value: 1, 4, 7, 10, 13, 16, 19, 22, 25, 28. Then we wrap around and go to 3, 6, 9, so on, so forth. This generates all the values for this. But the idea here is that the reason we'll use this as a test value is that if we do hello as our input and you use this as your initial deck setting, then you should get SNISY or snizzy as your output. So there's a lot that goes go specifically about this. All right, so I'm sorry for like going over this super fast, but also rambling a bit. You know, again, I'm still sick, so therefore a bit more tired than I reckoned I was actually before I started the lecture. So it's a good thing that I did not come into class today. All right. So any questions about all this before, because I know that took up a lot of time, but I wanted to make sure I got the chance to go over this. I will set the due date. You're going to have at least a week and a half to work on this. So it will probably be due sometime in week 6. This is currently week 4. But how is everybody? So any questions about this, or just planning on asking me questions when you get to it? Do we have to alter the original add method / constructor? The constructor, maybe. You are allowed to modify the constructor. You don't need to. And the add method, the one that just simply says add to the end, you probably don't need to touch that other than change the false to true. All right, so go ahead.
Yeah, did you set a due date for the Bigo assignment?
Did I not? Oy, okay, give me 1 sec. Apparently, wow. Apparently I did not. So, wait, no, I did. September 13th. So today, apparently.
Okay.
If people still need more time on it, that just let me know. Like, how many of you still think you need more, considerable more time? Like an extra day or so?
I need a bit more time.
Yeah, that'd be nice.
Okay.
I have a question.
Yes.
You mentioned that for the solitary encryption, it's recommended that we implemented the add and set method.
The get and set method, yes.
Oh, the get and set. What's the difference between the get and the get node method in this case?
The get node returns the node. It is an internal method, basically used only by the list, because your user shouldn't be able to interact with your nodes at all.
Oh, so
the get
both
returns the item that's actually being stored, and that's what the user actually cares about.
So then the get and the set is a static method, right?
No, they're public instance methods, whereas your get node is a private instance method.
I see. I see.
Static is only useful if it's basically not specifically tied to any instance of a class.
Oh, okay.
All right. So what I'm going to do for the remaining half an hour is as follows. I'm going to split you up into breakout rooms because I find this is the easiest way to do stuff. First off, if you have nothing to show me or nothing you want to ask me, or you just want to get out of here, you're more than welcome to sign out. Otherwise, what I'm going to do is I'm going to split you up into breakout rooms rather than trying to handle everybody in a pile. You can, well, technically, I'm going to create multiple breakout rooms. You are allowed, and you can go to them as you wish. I'll go through them in order. If you want to demo things, you can share your screen in the breakout room. Otherwise, you can ask me questions. All right. Otherwise, if you have nothing you want to discuss with me today, class is dismissed. Hopefully I will be here on Thursday. If not, I will let you know. Okay. Yeah, I'm fine except for feeling tired and being a bit snotty. So